What if the computers of tomorrow could break the rules of reality itself? This isn't science fiction, it's quantum computing. Imagine a computer so powerful it could design new medicines in days, not decades. Picture a machine that could create materials we have only dreamed of. This is not science fiction. This is the promise of quantum computing. The world is on the edge of a new technological era. This shift is happening quietly, inside shielded labs and supercooled chambers. Most people do not see it. But its effects could change everything. It rests on rules unlike the computers we use every day. So what is quantum computing? And what will it mean for us? Your laptop, your phone, even the world's biggest supercomputers all run on the same idea. Bits. A bit is a switch. It is either on or off, represented by a 1 or a 0. Quantum computers do not use bits, they use qubits, quantum bits that follow the laws of quantum physics. These laws govern the universe at the smallest scales, atoms and subatomic particles. Understanding this technology is crucial. It holds enormous potential. A qubit is not limited to just 0 or just 1. It can exist in a superposition, a state that encodes information about both possibilities at once. This is not flipping back and forth. It is a well-defined quantum state with measurable probabilities. A single qubit carries more information than a single classical bit. With 2 qubits, superposition spans 4 combinations simultaneously. With hundreds of qubits, the number of possible values exceeds the number of atoms in the known universe. Quantum computers are not just faster computers. They process information in a fundamentally different way. Qubits are extremely delicate. Any interference, noise, can destroy their state. Labs isolate them from heat, vibration, and electromagnetic fields. Systems run near absolute zero, colder than deep space. Building stable qubits is one of today's great engineering challenges. Quantum computing is built on quantum mechanics. In this realm, particles show wave-like interference. Particles can exist in multiple states until measured. They can also be entangled. Their outcomes correlated across distance. These are not abstract ideas. Engineers harness them to build machines. We will cover the science, the applications, and the risks. Potential benefits span drug discovery, materials, and finance, but the same power can also break today's cryptography. A quiet revolution is underway, and it affects everyone. Let's move from principles to impact. Some problems are beyond classical reach at realistic timescales. Molecular simulation is one of them. Even small molecules push classical limits due to quantum interactions among electrons. Quantum computers run on the same physics, enabling faithful models. This could speed drug discovery and reduce trial-and-error experiments. They could help design materials with tuned properties, catalysts, better batteries, new superconductors. Optimization problems are everywhere: shipping, factories, finance. When choices explode combinatorially, quantum algorithms may search more efficiently. In finance, better solutions could mean better risk management. Quantum is a specialized tool, not a replacement for your laptop. Classical systems will orchestrate workflows, offloading hard subproblems to quantum processors. The goal is practical advantage on defined, high-value tasks. Advanced simulation could support climate modeling and energy systems. Bottom line, quantum matters because certain problems are simply out of reach for classical alone. Quantum computers also pose a serious risk. Breaking widely used encryption. Private messages, bank transactions, and secure websites rely on cryptography. Many systems are easy in one direction and hard to reverse, like factoring large numbers. This hardness underpins RSA, securing much of the internet. In 1994, Peter Shor devised a quantum algorithm that factors efficiently on a large, stable quantum computer. A powerful quantum machine could break such encryption in hours or days. That would end the confidentiality of secure communications. Government, corporate, and personal data would be vulnerable. Adversaries can store encrypted data now and decrypt it later. The response is post-quantum cryptography. Algorithms believed hard for both classical and quantum computers. Migrating the internet to PQC will take years and global coordination. It is a race between quantum progress and quantum-resistant security. This is why quantum has become a matter of global strategic importance. The race spans corporations, governments, and universities worldwide. Major players include Google and IBM, among others. In 2019, Google's Sycamore performed a targeted task in about 200 seconds, estimated at thousands of years on a classical supercomputer. The claim was debated, but it marked real progress. Today the focus is quantum advantage, solving useful tasks better than classical. China invests heavily, startups pursue diverse hardware, superconducting, trapped ions, photonics. Progress is not just about more qubits. Quality, coherence, error rates, and connectivity matter. The goal is fault tolerance with error correction, to run complex algorithms like Shor's reliably. Quantum computing and AI are often linked, but we need clarity. Quantum computers will not create consciousness or general intelligence. They may accelerate specific math used in machine learning. Potential gains include faster optimization and sampling. Today's devices are too small and noisy for large AI gains. Research continues. In the future, quantum processors could act like accelerators, co-processors for the hardest math in AI pipelines. If realized, this partnership could shorten training cycles and improve models, not by magic, but by math. Quantum computing might redefine what's possible and what's dangerous. The question is, are we ready for it? Until next time, stay curious.